Welcome to video number 27 in the game theory sequence. In this video, I will start talking about games of incomplete information, and I will focus on static games or strategic form games, and on the case of one-sided incomplete information or one-sided uncertainty. So the theory of games of incomplete information deals with situations where at least one player is not quite sure what game she's playing. And we will see how to model this. Now, the way we model it is by using the structures that we introduced before, the interactive knowledge structures. So this can be used to model any kind of uncertainty in the mind of one or more individuals. So let's consider, for example, a situation where there are two individuals. One is myself, denoted as I, and the other individual is Anne, maybe a student, and I have two states. So we have a set of states, in this case 2, a partition of the set of states for each individual. In my case, it's the finest partition. Each state is in an information set containing that state only. And in the case of Anne, it's a trivial partition. There's only one set in the partition as the entire set containing both states. So if we hide what it says at the top, then, let me take away the, oops. If you look at just this structure, this abstract structure, you don't know what I'm talking about, right? There is uncertainty. Anne does not know if the state is alpha or beta, whereas I know that if the state is alpha, then I know that the state is alpha, and so on. But now we can interpret a structure like this by describing each state. So here I want to talk about the spelling of my name. It's common for people to misspell it. So I interpret one state, state alpha, as in terms of the one possible spelling of my name, which is one N first and two N's second. And then I interpret state beta in terms of a different spelling of my name, two N's first and one second. Then we want to indicate what the correct spelling is. So we designate one state as the true state, state alpha. So the correct spelling of my name is one N first and then two N's after the A. Okay, so, and then what does this situation represent? It represents that I know the spelling of my name, but Anne doesn't. Anne thinks that the spelling might be one N first and then two N's, or might be two N's first or one and one N second. So what else can we say about this? Well, we have that Anne, let me write here. So Anne knows that I know the spelling of my name. So Anne doesn't know what the correct spelling of my name is, but she knows that if it is one N first and then two N's, then I know that it is one N first and then two N's. And if it is two N's first, then I know that it is two N's first. So although Anne does not know what the correct spelling is, she knows that I know. Also, it's common knowledge between us that the spelling of my name contains three N's. It's just a matter of where to place them. There are 3 n's in the spelling associated with state alpha and 3 n's in the spelling associated with state beta. So since the common knowledge partition, if we write it here, the common knowledge partition would coincide with n's partition. And so whatever n knows, then it is common knowledge between us. So in particular, that the spelling contains 3 n's. So something is known to an individual if it is true at every state, and something is and the individual is uncertain about something if it varies from state to state. So Anne knows that there are 3 n's in my name, but doesn't know where they're placed. On the other hand, I, having the finest partition, always know everything. We could make it a little bit more complicated by adding a third person who thinks that in fact there might be 4 n's. Then we add Bob, and you know, this part is still what we had before, right? Now I'm adding a third state, and so it has to appear in the partition of every individual. And I put all 3 states in the same information set for Bob. So Bob, while Anne knows at the true state alpha that there are only 3 n's in my name, Bob doesn't. Bob thinks it might be either 3 or 4. It is still common knowledge at state alpha between Anne and me that there are only 3, but it's no longer common knowledge among the 3 of us that there are only 3 n's, because Bob thinks there might be 4 n's, and so on. So we can use these abstract structures, interactive knowledge structures, to talk about anything. So this might not be of particular interest to you, but in game theory, it is interesting to be able to model situations where, say, one player knows what game is being played, but another player has some uncertainty about it. In an incomplete information game, so incomplete information in game theory refers to a situation where at least one player is uncertain about some element of the game. Okay, so notice the difference between incomplete information and imperfect information. This is different from imperfect information. We use the expression imperfect information within the context of an extensive form game or a dynamic game to refer to the fact that at least one player, when it is her turn to move, does not know what happened up to that point. Maybe has some partial information about it, but is uncertain about some past moves of her opponents. Incomplete information, on the other hand, refers to uncertainty about the game itself. So about uncertainty about some elements of the game. Could be one or more, so some element or some elements of the game. So what are the elements of a game? So think in terms of strategic form games. how do we define a strategic form game? What do we need to specify? One is the players. We need to say how many players there are and who they are. Now, we normally call them players 1, 2, and 3, or we call them Anne, Bob, and Carla, whatever. But we specify the set of players. Then we need to specify for each player his set of strategies. What is it that that particular player can do? Then we specify the outcomes, the possible outcomes. And we need to specify how each player ranks the outcomes. So if there is at least one player who has some uncertainty about at least one of these elements, then we call the situation that we are describing a situation of incomplete information. Notice that I didn't use the expression game of incomplete information. I used the expression situation of incomplete information. The trick will then be to convert this situation of incomplete information into a game. So the theory of games of incomplete information was developed by John Harsanyi, another difficult name to spell, who was at UC Berkeley. He got the Nobel Prize in 1994, together with John Nash and Reinhard Zelter. Okay, so let me give you examples of a game of incomplete information. Suppose that some criminals have attempted to rob a bank, but the police arrived before they could escape, so they closed themselves in the bank and they took some hostages. So we have a hostage situation. So who are the players in this game? Well, the police on one side, and then the hostage takers, the criminals, on the other side. Now, they know how many of them there are. Maybe there are 5 of them, but the police might be uncertain as to how many there are. The police might think that there may be 2 or 1 or 5 or 20. Right? So this would be a situation of incomplete information where one player, the police, is uncertain about who the other players are or how many other players there are. Now let's look at the second element. When we describe the set of strategies for each player, we essentially say what each player could possibly do. Now imagine that the police have started a line of communication with the hostage takers, and the hostage takers say, bring us a helicopter for us to escape in, otherwise we will blow up this entire place. Okay? So they claim to have the ability to blow up the bank. So they claim to have a bomb. Now, the police might be uncertain as to whether, in fact, the hostage takers have a bomb or not. If they don't, then it's an incredible threat. They can ignore it. If they do, then it's a very different game. Now, typically when you are uncertain, you tend to attach probabilities to the various possibilities. So if the police is uncertain about whether the hostage takers have a bomb or not, they could say, well, you know, if they were planning a regular robbery, they didn't expect to be caught, why would they be carrying a bomb? So maybe we attach a very low probability, only 5% probability that in fact they do have a bomb, and 95% probability that they don't. Uncertainty about the outcomes. Well, this is also connected to what I said before. They don't know if a possible outcome is one where they blow up the entire bank, or if that is not a feasible outcome. if they plan to storm the place, they don't know if they will be able to enter the bank or not. So that's uncertainty about the possible outcomes. The uncertainty about how each player ranks the outcomes. So suppose that the hostage takers have said, instead of saying we'll blow up the bank, they've said bring us a helicopter, otherwise we will shoot all the hostages. Right? Now that's something they most likely can do, but then the police can be uncertain as to whether they will do. Right? So that means how do, as uncertainty about how do the hostage takers rank the outcome where they are caught without having killed anybody to the relative to the outcome where they're caught having killed a whole bunch of people. Very different outcome from that point of view, because in one case maybe they'll spend 10 years in prison, in the other case maybe they'll be sent to the electric chair. So any situation like one of the ones I've described is a situation of incomplete information. Now Harsanyi argued that we could in principle reduce everything to uncertainty about the last element, how people rank the outcomes. So I'm not going to go into the details of this, but he developed this theory by looking at the case where there is no uncertainty in the mind of anybody about who the players are, what each player can do, and what the possible outcomes are. The uncertainty is how about how the players rank the outcomes. So in principle, one player, say player one, should know how he feels about the outcomes, right? How he ranks the outcomes, but it's quite plausible to think that he might be uncertain as to how the other player, say player two, ranks the outcome. So this is a case where uncertainty is about payoffs. So uncertainty about payoffs. How do we represent a situation of incomplete information where at least one player is uncertain about what the payoffs are? So just take the structure I had before that dealt with the spelling of my name, but now change it by describing each state not in terms of how to correctly spell my name, but in terms of a particular game. So this is what I've done in this picture here. There are two possible states, alpha and beta. In both states, we have a two-player strategic game where player one can play either T or B and player two can play L or R. So all these two elements don't differ across states, so this they're common knowledge among the players. Let's see if there is anything else that is common knowledge among the players. Let's now look at the payoffs, and let's look at the payoffs of player 2. The payoffs of player 2 are from TL, TR, BL, BR in that order. 6, 18, 6, 0 in the game on the left, and also 6, 18, 6, 0 in the game on the right. So the payoffs of player 2 are common knowledge. Right, so we have that the payoffs of player 2 are common knowledge. In this case, the common knowledge partition, as pointed out before, coincides with the partition of player 2. So whatever player 2 knows is common knowledge. So it's common knowledge between players 1 and 2 that they're playing a game where one chooses between T and B and player 2 chooses between L and R, and player 2's payoffs are 6, 18, 6, 0 from TL, TR, B, L, BR. Okay. Now, if we look at the payoffs of player 1, on the other hand, in one game they are 0, 9, 9, 0. In the other game they are different. They are 18, 0, 9, 9. So let me use different colors so it's more evident that they are different. 18, 0, 9, 9. So the payoffs of player 1 are not common knowledge. And what is the case here? That 2, so 1 knows her own payoffs. If the payoffs of player 1 are 0, 9, 9, 0 state alpha, then since the information set containing alpha for player 1 is just the singleton set alpha, player 1 knows that her own payoffs are 0, 9, 9, 0. If, on the other hand, the payoffs are 18, 0, 9, 9, as described in state beta, then again, since player 1's information set containing beta is just a singleton set containing beta, it means that 1 knows her own payoffs also in that state. On the other hand, player 2 is uncertain about 1's payoffs, but knows that 1 knows. So I don't know if the state is alpha or the state of beta, but I know that if the state is alpha, then player 1 knows that the state is alpha, and if the state is beta, then player 1 knows that the state is beta. Now, as external observers or as modelers, we want to know what the true payoffs of player 1 are, right? And that's why we designate one state as the true state. In this case, I designated state beta as the true state, meaning that, in fact, the players are playing the game associated with state beta, where the payoffs of player 1 are 18, 0, 9, 9. Player 1 knows this, player 2 doesn't. Player 2 thinks that there is a possibility that they're playing that game, but there is also a possibility that they're playing a different game where the payoffs of player 1 are 0, 9, 9, 0. Now, one extra thing that we do is then, when there is uncertainty in the mind of the players, we then attach probabilities to the possibilities that the player has in mind. So in this case, player 2 assigns probability 1/3 to the state being beta and 2/3 to the state being 2/3. And when I say the state being beta, I mean them playing the game associated with state beta, and similarly for state alpha. And also I'm going to assume throughout, as Harsanyi did, that these are von Neumann Morgenstern payoffs. So this is a cardinal game. Now the true state is for completeness, it's important to say what game is actually being played, right? But surprisingly, it's an element that is missing from Harsanyi's theory of incomplete information. And you'll see why, because whether we designate state alpha as a true state or state beta as a true state, it doesn't matter in terms of what Harsanyi is suggesting to do to model a situation like this. But I think it was an oversight. I think one should always indicate what the true state is. It's obvious when we talked about the spelling of my name. Only one of the two is correct, and we should indicate which one is the correct one. So what did Harsanyi suggest we do in a situation like this? This is clearly, the picture you're looking at is clearly not a game. It's a collection of games. In this case, there are 2 games, and together with some states called alpha and beta, and some information partitions for each player and so on, but this picture is not a game. So Harsanyi said, well, we can transform it into a picture that is a game. So we can transform it into a game. And so this is called the Harsanyi transformation. See, I also don't remember always Harsanyi, what the correct spelling is. I think that's correct spelling. So the Harsanyi transformation what we do is we construct an extensive form game where the first move is a move made by nature. And what does nature choose? Nature chooses the game or the state. Right? So either chooses state alpha or choose state beta. Whenever we have a move of nature, we need to associate with it a probability. And as probabilities, we take the beliefs of player 1. This we can do in the simple case. Later on, we'll see that it's a little bit more complex in the case where the situation of incomplete information is not one-sided. So we start with the move of nature, and then we let player 1 know what the state is, because that's what the picture says, that if the state is alpha, then player 1 knows, and if the state is beta, then player 1 knows. So we have a node where player 1 chooses between T and B, knowing what the state is, so essentially knowing what the game is. And then we want to make, of course, player 2 move and choose between L and R, but reflecting two kinds of uncertainty in the mind of player 2. First of all, the game represented there as a simultaneous game, so player 2 is not told what player 1 did, so we need to represent the uncertainty in the mind of player 2 about what player 1 did. And also, we need to reflect, to represent this uncertainty that player 2 has about what game is being played. So essentially, we don't tell player 2 anything. We say player 2 has an information set where when she chooses between L and R, she doesn't know what player 1 chose, and she doesn't know what nature chose. She doesn't know what game she's playing. And we now put the choices of player 2 and R. And now the last thing we need to do is add the payoffs. So let me make this a little bit smaller. Okay, so we have to take the payoffs from the picture above. So what is the payoff from TL? Well, it's 0, 6 if the state is alpha, but it is 18, 6 if the state is beta. Payoff from TR is 9, 18 if the game is the one associated with state alpha, but it is 0, 18 if the state is beta, and so on. So TR, and then we have BL, 9, 6 in both cases. And then we have 0, 0 from BR as state alpha, but we have 9, 0 as state beta. Okay. And so we have now constructed a natural game where we have represented the situation of incomplete information that we have above. So now this is a game with imperfect information. Right? Imperfect information because player 2, when she decides between L and R, she doesn't know what player 1 did, and she doesn't know what nature chose. And so the idea of the Harsanyi transformation is to convert incomplete information into imperfect information with this trick that we start the game with a move of nature. Now you can see that the picture we would have drawn, the game we would have drawn, would have been exactly the same if the true state had been alpha. Right? There's nothing in the game that Harsanyi suggested that tells us what the true state is. Of course, we could add that information, maybe put the beta in a square and say the square means this is the true state, but this is not what Harsanyi did. And so this is why in the end the designation of one state as a true state doesn't really matter from the point of view of Harsanyi's theory. What Harsanyi then suggested was solving this game using the notion of Nash equilibrium, which he then called a Bayesian Nash equilibrium. So let's first of all see how we would solve this game using the notion of Nash equilibrium. So first of all, we have to identify the set of strategies for each player. So let's call S1 the set of strategies of player 1. And remember the definition of strategy. A strategy in an extensive form game is a list of choices, one for every information set of that player. So if player 1 has 2 information sets, each consisting of only one node, so we have to specify in a strategy what player 1 does at the information set on the left and at the information set on the right. So TT is one possible strategy, TB is another one, BT and BB. Now, if you don't specify anything, then the default interpretation would be, if I look at TB, for example, the first says what player 1 would do at the left node, and B would be what he would do at the right node. Right? So we interpret strategies by looking at information sets from left to right and then from top to bottom. On the other hand, player 2 only has one information set, so strategy of player 2 just gives us one choice, and that choice can be either L or R. So player 2 has 2 strategies. So if we draw the strategic form, then what we need is a table with two columns. Because player 2 has only 2 strategies, we label one column L, the other one R, and this would be player 2 moving, and 4 rows, and we label them with the strategies of player 1, which are TT, TB, BT, and BB. And then we need to put in the payoffs there. So let's take, for example, this strategy profile here, BTL. So what does that mean? BT, the first one refers to the left node, so B there and T there, and player 2 plays L. And then what are the payoffs? Well, they could be 9-6 or they could be 18-6 depending on what nature chooses. So the payoff of player 1 one's payoff in that cell is 9 with probability 2/3 and 18 with probability 1/3. So with probability 2/3, nature chooses alpha, and then we go down to BL and we go down to payoff of 9 for player 1. And probability 1/3, nature chooses beta, so then we go down to, following TL, we go down to 18. Now this is where the assumption of von Neumann-Morgenstern payoffs is relevant, is that we can compute an expected payoff. So it's 9 times 2/3 plus 18 times 1/3. So it's 6 plus 6 is equal to 12. So we put a 12 here as a payoff of player 1. What about the payoff of player 2? Payoff of player 2, let's go here. 2's payoffs is where with probability 2/3 we pick the payoff on the left, so 6, and with probability 1/3 we pick the payoff on the right, which is also 6, so this is equal to 6. So the payoff of player 2 in that case is 6. Okay. So I'm not going to go through all the calculations. I encourage you to pause the video here and compute the payoff of player 1 for each cell and the payoff of player 2 for each cell, and then restart and see if what you computed coincides with what I'm writing now. Okay, so the payoffs are for player 1, 6, 6 in the first row, 3, 9 in the second row, 12, which we already computed, and 0 in the third row, 9 and 3 in the fourth row. The payoffs of player 2 are 6, 18, 6, 12, 6, which we already computed, 6, 6, 0. So this is a cleaned up version of the table, removing all the side annotations, and then we can look for the Nash equilibria, and we have that BTL is a Nash equilibrium. Given that player 2 plays L, then player 1 does the best with BT, and given that player 1 plays BT, then player 2 gets the same payoff with L and R, so L is a good choice. Is the best reply to BT, so BTL is a Nash equilibrium, and there is also another one which is TBR. So two Nash equilibria. Harsanyi called these so two Nash equilibria. One is BTL, the other one is TBR. Harsanyi called them Bayesian Nash or Bayes Nash equilibria. This expression has become common in the literature. So when you see this is a Bayes Nash equilibrium of a game, or a Bayesian Nash equilibrium of a game, then you should just understand it as Nash equilibrium. There's no difference between Bayesian Nash and Nash. The only thing is that if you hear the expression Bayes Nash or Bayesian Nash, it's a hint that the game you're looking at comes from a situation of incomplete information. It's supposed to represent a situation of incomplete information. So let's now talk a little bit about this equilibrium. Notice that at the time when Harsanyi was developing his theory of incomplete information, Nash equilibrium was the only solution concept that was known. right? So no surprise here that he suggested solving the game using Nash equilibrium. To use the notion of Nash equilibrium, we have to go through this lengthy process of constructing a strategic form and then computing the expected payoffs for each cell, which requires time. An alternative would be to look for the weak sequential equilibria of this game. And then we know that if we find a weak sequential equilibrium, which is a strategy profile with a system of beliefs, then the strategy profile itself is a Nash equilibrium. So that would be a quicker way of calculating the Nash equilibria. And it has the advantage that in some games it eliminates some bad Nash equilibria. Now, this is a game where no matter what strategies the players choose, every information set is reached with positive probability. And when I was talking about weak sequential equilibria, I said that in this class of games, where every information set is necessarily reached with positive probability, there is essentially no difference between weak sequential equilibrium and Nash equilibrium. So if you find all the weak sequential equilibria, then you found all the Nash equilibria as well. And this particular game that you're looking at in extensive form is in fact the game that I looked at in the videos on weak sequential equilibrium. So to find the weak sequential equilibrium of this game, what you should do is find them and then go back and check if they match what I gave as equilibria in the video on weak sequential equilibrium. But we already know that the answer has to be that this game has only two pure strategy weak sequential equilibria whose strategy component have to be either BTL or TBR. I want to conclude this video by commenting on how we should interpret this Nash equilibrium. So what is the interpretation of a Bayesian Nash equilibrium, or a Nash equilibrium of a game obtained by applying the Harsanyi transformation to a situation of incomplete information? So we looked at BTL before. Let's pick the other equilibrium, TBR, and let's think about it. So TB says player 1 chooses T on the left and B on the right, and player 2 chooses R. Okay. So this is TBR, right? Is a Nash equilibrium of this game. Right? But this is not the game that the players are playing, right? We designated before state beta as the true state, right? Meaning that the true game, the game that they are actually playing, is the game associated with state beta, where the payoffs are from TL 18 0 from TR 0 18 from BL 9 6 from BR 9 0. So as a matter of fact, they end up playing BR in this, the true game, which is not a Nash equilibrium. Of this game. Right? Because if player 1 plays B in this game, then player 2 would want to play L, not R. So R is not the best reply to B. So why is it that they end up not playing a Nash equilibrium? And the answer is very simple, is that while player 1 knows that he's playing this game, and so his choice of B is the best reply to what player 2 does, player 2 does not know that she's playing this game. She thinks there's a probability 1/3 that she's playing this game, but also probability 2/3 that she's playing a different game with different payoffs. So although TBR is a Nash equilibrium of the entire game, what they end up playing in the actual game associated with the true state might not be a Nash equilibrium of that game. But that is not a problem, because it's just a reflection of the fact that player 2 is operating under uncertainty and does not know what game she's playing. What seems to be more puzzling is the fact that the strategy of player 2 is tells us, so one strategy in the extensive game is TB, right? To be understood that player 1 would play T if the state is alpha, and B if the state is beta. But in the situation we represented initially, player 1 knew that the state was beta. The true state is beta, and player 1 knows that the state is beta. So why should player 1 bother to even think about what he would do in a game that he knows he's not playing? Why would he need to think about what strategy would choose in the game associated with state alpha when he knows that the state is not alpha, he knows that the state is beta? So it's like saying, I'm planning to go either to San Francisco or Los Angeles next month. It makes sense for me now, not knowing where I will go, to decide where I would go, where I would stay if I went to San Francisco, if I went to Los Angeles. But imagine that, in fact, I am in San Francisco. I know that I'm there. It's just somebody else doesn't know where I am, right? I didn't tell them, so they think I might be in Los Angeles or in San Francisco. Well, I, being in San Francisco, don't need to think about where I would stay if I was in Los Angeles. Why would I want to even think about that? Right, so what do we require player 1 in this game to say what he would do if the state were alpha when he knows that the state is not alpha? So why do we require a strategy of this form? And the answer is, well, because the strategy of player 1 plays a double role. So part of the strategy tells us what player 1 actually does, which is to play B, because he knows the state is beta, and in the game that he knows he's playing is playing B. The other part of the strategy, the T, that refers to the other state, the game associated with the other state, state alpha, is actually more a representation of what is in the mind of player 2 about what player 1 would do in that situation, because from the point of view of player 2, both possibilities are there. Both the game that is associated with state alpha and the game that is associated with state beta. So player 2 has to ask herself, what would player 1 want to do in this game associated with state alpha, and what would player 1 want to do in the other game? So the strategy of player 1 plays a double role, tells us what player 1 actually does, and part of it tells us what player 2 thinks player 1 would do. And so I hinted at this possible interpretation of a strategy earlier on, and it becomes very much more relevant and important in the context of games of incomplete information. Okay, so I will, in the next video, deal with situations of incomplete information that reflect double uncertainty in the mind of not only one player but both players. So that's called two-sided incomplete information, or multi-sided incomplete information if there are several players. But I will kind of cut short this topic of games of incomplete information, because to proper test you on these topics, I would need you to draw games and go from a description to a representation and so on, which cannot really be done in online quizzes. So I will replace an extensive treatment of games of incomplete information with some other topics.